here we go. On section 5.3 lab, the first several problems are just logarithmic and exponential equations that we need to solve. And then on the back, there are a couple of word problems. So starting off with problem 1a, it says solve each equation algebraically. Log base 2 of 3x plus 5 equals 4. Remember, when we have logarithmic equations, the idea is we want to get the equation or each side of the equation simplified so that we either have our log is equal to some number or your logarithm is equal to another log with the same base. This is a case where we have a logarithm is equal to a number. When we get to this point, we can use exponential equations to solve. So we're going to convert this logarithmic equation to an exponential equation. Log base 2 of 3x plus 5 equals 4. This is equivalent to 2 to the 4th power equals 3x plus 5. All right, our base, we raise that to the number that the logarithm is equal to and set that equal to the term that we're taking the logarithm of. All right, then from here, 2 to the 4th power would be 16. So this gives us 16 is equal to 3x plus 5. And this is a simple linear equation. First, we subtract 5 from both sides, and that gives us 11 is equal to 3x. And then we would divide both sides by 3. So 11 over 3 equals x. That's the solution. With logarithmic equations, you do always want to go back and make sure your solution works, especially if you end up getting a negative number. Negative answers don't always work. Here, if we plug in 11 over 3, that works. You can only take the log of something positive. So if you plug in your answer and the term that's in parentheses there becomes negative, that means that it's not an actual solution. It's an extraneous solution. All right, one down. On to part B. Log of x plus log of x plus 3 equals 1. Now, in this problem, if you notice on the left-hand side, instead of just having one logarithm, we have the sum of two logs. We want to use properties of logs to try to condense that side to just one logarithm. So we have a property that tells us that log of x plus 3 would be log of x times x plus 3. I'll just write it this way. And then simplifying that a little bit more, we get sorry, you guys. Simplifying this a little bit more, we get log of x squared plus 3x equals 1. All right, now from here, once you have a logarithm is equal to a number, then you want to convert to exponential form. Here we have the common log, which is base 10, even though the 10 isn't written. So this would be 10 to the 1st power equals x squared plus 3x. All right, this gives us 10 is x squared plus 3x. This is a quadratic equation, so we need to move all of the terms to one side. 0 equals x squared plus 3x minus 10. And then if we factor this, we get x plus 5 times x minus 2 is equal to 0. Setting these factors to 0, x plus 5 is 0, x minus 2 is 0. This gives us x is equal to negative 5 and x is equal to positive 2. All right, now remember, I said we want to always check to see if both of the numbers actually works. If we plug in 2, we get log of 2 plus log of 2 plus 3. That's log of 2 and log of 5. We can evaluate both of those, okay? If we plug in negative 5, we cannot compute the log of negative 5. You can only take the log of positive numbers. So that means that negative 5 isn't an actual solution. And x equals 2 is the only solution. All right. Any questions so far? Then on to part 2. In question 2, we're given exponential equations and asked to solve these algebraically. With an exponential equation, that's where you have your variable being an exponent of your problem. You have to find a way to get it down. To solve an exponential equation, we're going to use logarithms. All right, so for 4 times 5 to the 3x plus 2 equals 6, your first step is to isolate the exponential term. So that 5 to the 3x plus 2 power, we need that on one side of the equation by itself. We do that by dividing both sides by 4. So we get 5 to the 3x plus 2 equals 6 over 4. You can leave that as a fraction if you want to, or you can write it as a decimal if the decimal is a terminating decimal. So 6 over 4 would be 1.5. If it was like 1.44444, leave it as a fraction instead of converting it to a decimal. All right, from here, once you have your exponential term isolated, remember our goal is to solve for x. That x is stuck up in the exponent. We have to bring it down some way. We can't just pull down exponents all willy-nilly when we want to. However, there is a property of logs that allows us to do that. So we're going to introduce logarithms into the problem so that we can use that property. If 5 to the 3x plus 2 equals 1.5, then log of 5 to the 3x plus 2 power equals log of 1.5. Now, our power property of log tells us that the left-hand side is 3x plus 2 times log of 5. And that would be equal to log of 1.5. From here, we need to solve for the x. So there are a few steps we need to do. We've gotten it down. Now these are just a couple of algebra steps. We'll need to divide by log of 5. So 3x plus 2, you can keep it in the parentheses or not, equals log of 1.5 divided by log of 5. And then if we subtract 2 from both sides, 3x equals log of 1.5 divided by log of 5 minus 2. And then finally divide everything by 3. X equals log of 1.5 divided by log of 5 minus 2, all, make that squiggly, all divided by 3. I always write it all out like this and then use the calculator at the end. If you want to use your calculator in the middle to like divide the log of 1.5 by log of 5 first, get a decimal, that's fine too. We should all get the same answer at the very end of the problem, which is, let's see, I got that x is equal to negative 0.563, or around 3 decimal places. What does the direction say? 2 is what the direction said. And I had the wrong number anyway. It's negative 0.58. Then on to 2b. 200 e to the 0.5x equals 50. Again, our first step in this problem would be to isolate our exponential term. So we'll divide both sides by 200. 50 divided by 200 would be 0.25. So this gives us e to the 0.5x equals 0.25. All right, from here, since we have an exponential term with base e, we're going to want to bring in logs because we have to bring down our log or our exponent at some point. If you have base e, you want to use the natural log. So this would be ln of e to the 0.5x equals ln of 0.25. Then from here, if we bring down the exponent, 0.5x times ln of e equals ln of 0.25. Now, ln of e, that term just simplifies to 1. So this is 0.5x is ln of 0.25. And last step, divide both sides by 0.5. All right, so ln of 0.25 divided by 0.5. This gives us that x is equal to negative 2.77. All right, then on to the back. So in problem number 3, we have a nice word problem here that requires us to use exponential equations to solve. S equals 50,000 e to the negative 0.8x models the decay of sales for a given product over time in months since a certain ad campaign was used. So basically, this is saying that for some company, they ran an ad campaign like a commercial, right? And when they did that ad campaign, of course, that would increase sales. But once that stopped, over time, their sales started to decrease. So that's what this is saying. It models the decay of their sales after that ad stopped running. Okay. The question is, how long will it take for the number of cells to decrease by half? Solve algebraically. So we wrote this out in the at the end of the last class, that if you take that function s equals 50,000 e to the negative 0.8x, the 50,000 p represents the initial value. So the cells started out at about 50,000 cells, and then over time it decays. Half of that would be 25,000. So we're essentially just asking how long does it take for the output to become 25,000. We get 25,000 equals 50,000 e to the negative 0.8x. All right, let's solve this. The first step would be to not erase the problem. All right, divide both sides by 50,000. 25,000 divided by 50,000 is 1/2, or you can write it as 0.5. And we'll have 0.5 equals e to the negative 0.8x. An exponential equation. So from here, we want to take the natural log of both sides. ln of 0.5 would be equal to ln of e to the negative 0.8x. And I'm running out of space here, so I have to go to the other side. ln of 0.5 is equal to negative 0.8 x times ln of e. Remember, we said ln of e is 1. So this would just be ln of 0.5 equals negative 0.8x. And x would be equal to ln of 0.5 divided by negative 0.8. And this gives us 0. It doesn't say what to round to, but that's okay. 866. So that's our value of x. But this is a word problem, so we can't just say, oh, x is 0.866. We want to write out a sentence that explains what this value actually means. So I'll come over to the side to do this. We're told in the beginning here that x represents the, this is the decay. I'm sorry, the decay of cells over time in months. So x represents the months. That's pretty fast though. Well, yeah, okay, it makes sense. So this is saying after about 0.866 months. So after about 0.866 months, the cells will decrease or decay by half or decrease by half. So it won't take very long for this to go down by half. Now, a couple of things. At first, when I looked at this problem, I was thinking, that number sounds kind of small. but does it make sense? Is it a reasonable number? If we look at the exponent, we have e to the negative 0.8x. Remember, that exponent tells us the decay rate. So this is saying that the cells are decaying by 80% every month. So yeah, it would make sense. 0.8 is 80%. So it would make sense that in less than a month, it'll decay by half. All right. And then for part B, what does the model predict about cells 1 year from now? Solve algebraically and write a solution as a complete sentence. So 1 year from now, X would be equal to 12, because this is the decay for a product over time in months. So 1 year is 12 months. Then we'd get S is equal to 50,000 times e to the negative 0.8 times 12. Which gives us 3.38. Now, for interpreting this, we're not really given information about the nature of the sales, what kind of products we're selling. We're just told that you input the number of months and its function outputs the number of sales for the company. So usually you can't sell half of something. Sometimes you can, sometimes you can't. We can leave the answer as 3.38 and say the sales are 3.38. Or if you wanted to round to the nearest whole number, that would be fine too. Okay. So we'll say after 1 year, sales are down to about 3 units. We don't know what they're making, so, or selling, I should say. But woo, they should run that ad campaign again. This is a sad story. They started off with 50,000 sales, and then after a year, they're down to just 3. That's a big hit to business. I think they might need to afford to run those commercials once or twice again. All right. Then on to the last one here. Problem 4. Suppose you have deposited, or suppose you deposit. There we go. Suppose you deposit $3,000 at 5% annual interest compounded monthly. Write the equation that models the growth of the money if the equation for compound interest is future value equals P times 1 plus R over N to the NT power. Okay. How long will it take for the money to reach 5,000? Solve algebraically, write in a complete sentence. So we know that we're investing $3,000. P is 3,000 at 5% interest. R is 0.05, or you can just do 0.05. And then we're compounding monthly. So N would be equal to 12, because compounding monthly means 12. And T we don't know, which is okay. Our equation would be the future value is 3,000 times 1 plus 0.05 over 12 to the 12t power. All right, so if we plug in T, the number of years that we've made this investment, into this equation, it'll tell us how much money we have at the end of the investment. All right, part B, how long will it take for the money to reach $5,000? So in these types of problems, when you're asked to find the time or the length of time, notice the exponent T, or the value of T, is in the exponent. So you're asked to solve an exponential equation here. Anytime you're asked to figure out how long it takes to reach a certain amount of money in a compound interest problem, you're solving an exponential equation. So in this one, we know that the output will be $5,000. We know that the input was, I'm sorry, not the input, but the function was 3,000 times 1 plus 0.05 over 12 to the 12t power. And we want to solve this for t. To do this, first step, we want to divide both sides by 3,000. Why am I dividing both sides by 3,000? So that we can isolate the exponential term. All right, 5,000 divided by 3,000, that would give me 1.6666666 forever and ever and ever sixes. I do not want to write that around that number yet. You don't want to round in the middle of your problem. So I'm just going to keep that as a fraction, 5 over 3. 5,000 divided by 3,000 simplifies to 5 over 3. And this would be equal to 1 plus 0.05 over 12 to the 12t power. From here, once your exponential term is isolated, you want to take the log or natural log of both sides. Log of 5 over 3 equals log of 1 plus 0.05 over 12 to the 12t power. Bring down the exponent. Okay, and then from here, we have on the right-hand side, 12 times t times log of 1 plus 0.05 over 12. We want to divide to get t by itself. We take log of 5 over 3 and divide by 12, and also log of 1 plus 0.05 over 12. Then we've isolated our t. All right, now you just have to enter all of this into your calculator. And you do need to practice entering expressions that look like this into your calculator. We'll see them a lot in chapter 6 when we're solving financial problems like this one, where you have to figure out how long it takes to get to a certain output. All right, but this would be log of 5/3 divided by, if you type this into your calculator all at once, you need to put the entire denominator in parentheses. So parentheses 12 times log of 1 plus 0.05 over 12. And we got that this is about 10.24. And you always want to put years, or your units, which is years in this case. So in a sentence, it will take about 10.24 years for the money to grow to $5,000. That feels like a long time, but maybe not. All right. I want to do another couple of problems like the last one that we just did, where we have a compound interest problem and we know the output. We want to solve for the input. All right. So this is still section 5.3, and we'll just do a couple practice problems. So practice with solving applications with exponential equations. So first example, let's say $6,500 is invested into an account earning 4.3% interest. We'll do this a couple of different ways. So first, If interest is compounded quarterly, how long will it take for the investment to double? All right. So when we have a problem like this, we know that this is compound interest. We're compounding quarterly. We know we have a formula for compound interest. Remember, on your next test, and we don't really need it on this quiz, but on your quiz, I will give you a formula sheet. I think it's already posted on our Canvas page under modules. I'll double check. But the formula sheet has all of the compound interest formulas and the annuity formulas that we're going to learn. You don't have to have them memorized. You just need to know how to use them and what all of the variables represent. So in this one, our compound interest problem is we're compounding quarterly, so future value equals P times 1 plus R over N to the NT power. In this case, P is $5,600. Okay. What else are we given? We know that R is 4.3%, so that's 0.043. And then for the value of N, we're compounding quarterly. So these are the important things we need so far. Compounding quarterly. Quarterly is 4 times a year, so N would be equal to 4. And then the last variable there is T. T is what we're trying to find. And then this is the interesting part. We're asked to double our investment. Double 6,500 would be 13,000. So we're trying to figure out when the output or that future value is equal to 13,000. All right, let's put all of that information together. We want to solve the problem. Let's see, this is all my side work. 13,000. I'm going to use a different color so we can see better. All right, 13,000 is equal to 6,500 times 1 plus 0.043 divided by 4 to the 4 times T power. All right, I'll pause really quickly here so that you can make sure everybody understands what the numbers are. P, our principal, is 6,500. We want to know how long it takes to double that. So that means that the output would be 2 times 6,500. That's where the 13,000 comes from. R is 0.043, and then we're compounding quarterly, so N is equal to 4. Now, to solve this, we know that the variable T is in the exponent. We're going to have to isolate the exponential term, take the log of both sides, bring down our exponent, divide. It's the same process over and over. You just want to be careful to make sure that you don't, it looks kind of messy. It looks like it's a bunch of terms and decimals in there. What's this 1 plus 0.043 over 4 thing? You may want to simplify that a little bit more if you want, if you don't like to see the fraction written that way. That's up to you. The very first thing you need to do, though, to solve a problem like this would be to divide both sides by 6,500. So we'd have 13,000 divided by 6,500 equals 1 plus 0.043 over 4 to the 4t power. All right. Couple places here where you can simplify. 13,000 divided by 6,500, that's just 2. We're doubling. And then on inside of the parentheses here, 1 plus 0.043 over 4, that simplifies to 1.01075. And then we have that to the 4t power. So the problem actually simplifies quite nicely. All right, then from here, we're gonna run out of space, but that's okay. Once we have our exponential term isolated, so the left-hand side has our exponential, right-hand side, I'm sorry, has our exponential term isolated. Then we want to take the log or natural log of both sides. Let's go log. So log of 2 would be equal to log of 1.01075 to the 4t power. I'll pause here just in case anybody's still writing. Give you a few seconds to finish writing this part because we're going to need to go to the next page to continue the problem. 0, 1, 0. Okay. All righty. So picking up where we just left off in the last problem, I'm just going to rewrite it again. Our last step, log of 2 equals log of 1.01075 to the 4t power. The point of introducing logs is so that we can bring down that exponent. So this gives us log of 2 equals 4t log of 1.01075. And then there's only one more step. We have to divide. To get t by itself, we need to divide both sides by 4 log of 1.01075. And then calculator time. So we type this into our calculators. This gives us 16.21. All right. Now remember, with word problems like this, you always have to or want to write your final answer as in a sentence. What were we talking about 10 steps ago when we started this problem? What was our original question? I'm going to go back to the first page. We're asking, how long will it take to double the investment if our interest is compounded quarterly? So this is telling us our answer was about 16 or 16.21. It takes about 16.21 years to double your investment. So that's our answer. It will take about 16.21 years. You always want to make sure you include your units to double the investment. And that's our final answer for that one. Cool, let's do another one. So I feel like I can squeeze it in over here. This will be part B of the same problem. What if instead of compounding the interest quarterly, we compound the interest continuously? So if the interest is compounded continuously, how long will it take to double? All right, when we see compounded continuously, we should remember that we have a different formula for that. The formula for continuous compounding interest is future value equals P times e to the RT. Okay, and in this case, P is 6,500 still, R is still 0.043, T is what we're trying to find, but we do know that the future value will still be 13,000. So all that's changing here is our compounding frequency, but that changes the formula that we have. All right, this would give us 13,000 equals 6,500 times e to the 0.043 t, because we want to solve for t here. All right, then for solving, first step, divide by 6,500 to isolate the exponential term. Then 13,000 divided by 6,500 is 2. So we end up with 2 equals e to the 0.043t. And then once you have your exponential term isolated, you want to take the log or natural log of both sides. In this case, since our exponential term has a base of e, I'm going to use ln. ln of 2 is ln of e to the 0.043t. And that tells me that ln of 2 equals 0.043 t times ln of e. And remember, ln of e is just 1. So ln of 2 equals 0.043 t. And t would be ln of 2 divided by 0.043. Which is, run out of space here, so I'll write it over here. T equals 16.12 years. So notice here, the answer that we get when we compound continuously, what am I doing? Sorry, guys. The answer that we get when we compound continuously is slightly less than the answer that we get when we compound quarterly. What is that saying? If we compound continuously, we're able to reach our goal of doubling a little bit faster. That's because compounding continuously yields higher or better outputs, or yields more money. Or a better way to say that would be, your money grows faster if you're compounding continuously, slightly faster. So you'll double a little sooner than you would if you compound quarterly. Last step though, writing this in a sentence. It will take about 16.12 years to double the money in this case. Now, these types of problems where we have compound interest, or it really can be anything that's modeled exponentially, and you're trying to solve for the length of time, will always work out the same way. If you're trying to solve or figure out how long it takes to get to a certain amount of money, you're going to have to solve an exponential equation. So find the amount that you want, set that equal to your output. You're always going to, first step, divide by the principal. That should isolate your exponential term. Second step, take the log of both sides. Third step, bring down your exponent. And then fourth step will be to use the properties of just algebra to solve for your variable t. Depending on what your exponent is, that could take 1 or 2 or 3 steps. But it's the same kind of pattern. Okay. I want you guys to try one more of these. So I'm going to write one up. I'm going to give you a couple minutes to work on it. I do want you to actually try the problem, try to set it up, practice putting this information into your calculator the right way, and then we can see if we get the same answer. This would be example 2. If $7,255 is invested at 8.13% compounded, won't make it too bad, semi-annually. That's twice a year, so n equals 2. All right. How long will it take to grow to $10,000? I want you all to take a moment to set up this problem, think about what formula you would use, think about what variables you know, what's your unknown, and then try to solve this. All right, I'll give you a few more seconds to wrap this one up, and then when the clock strikes 9:22, we'll go through the solution together. All right, someone else also got 4.02, 4.03. All right, let's see what the answer is. So when you set this up, we should use the formula future value equals P times 1 plus R over N to the NT power. And I'll just come over to the side to write out what these values are. P in this case is $7,255. R would be 0.0813. N, which I told you is 2. If you're compounding semi-annually, that's twice a year. Okay, and then T, we don't know. We're trying to find that. And we see how long, that's solving for T. And then the future value is $10,000. So when we put all of this in, we should have 10,000 equals $7,255 times 1 plus 0.0813 over 2 to the 2t power. All right, first step, divide both sides by 7,255. Now, when you put this into your calculator and divide, I can't imagine it simplifies to something nice. It's 1.378359752. If you want to write that long decimal down, you can. Do not round though. Don't just write 1.38. Okay. I'm going to keep it as a fraction though. This would be 10,000 divided by 7,255. And that's going to be equal to, now this we can simplify, 0.0813 divided by 2 is 0.04065. So this would be 1.04065 to the 2t power. Now you may have left that term in the parentheses as 1 plus 0.0813 over 2. That's fine too. All right, let's see. From here, our exponential term is isolated. So we'll take the natural log ln of 10,000 divided by 7,255. That's going to be equal to ln of 1.04065 to the 2t power. Bringing down our exponent. On the right-hand side, we get 2t times ln of 1.04065. And then finally, ln of 10,000 over 7,255 divided by 2 times ln of 1.04065. All right, let's see what that is. So a few of you got this right. That's approximately 4.0, if you round to 2 decimal places, 4.03. And then in words, we'll say it will take about 4.03 years. Don't forget to indicate the unit of time for the money to grow to $10,000. The end.